Everybody. I don't know the time you're watching this video, but anytime you're watching it, I want to say hello to you. Okay, so without wasting my time, let's just dive deep to the main agenda of this video. Okay, so this video is for magnetism. So let's just go straight. Fields and forces of magnetism. So magnetism is a phenomenon associated with magnetic field, which arises from motion of electric charges. Okay, so let's break down this definition. Because what you are getting from here is magnetism is a phenomenon associated with magnetic fields. Okay, so which arises from the motion of electric charges. So what the definition is saying is magnetism occurs as a result of magnetic fields, and magnetic fields also arises from the motion of electric charges. So let's take the definition back. So from what the definition is saying, magnetic fields, we get magnetic field from the motion of electric charges. So anytime electric charges move or they are displaced from one place to the other, when there's a motion in electric charges, we get what we call magnetic field. And magnetic field is also associated with magnetism. So the definition of magnetism is uh, something that occurs as a result of magnetic field. And the magnetic field is also caused by motion of electric charges. So that's a simple and a brief definition of magnetism. It can also be defined as electric current in a conductor or charged particle moving through space. So the fact that electric charges or electric current is moving, it becomes magnetism. And also it can be the motion of electrons in an orbital, atomic orbital. So if electrons move in an atomic orbital, it is called magnetism. That's briefly what this slide is trying to talk about. Magnetism also can be defined as elementary particles such as electrons that have the property to spin. So if electrons uh, are able to spin, we also have what we call magnetism, because it is electron or electric currents or electric charges that are moving. Spinning means going around something. So if electrons also have the ability to spin, it is also related to as magnetism. Okay, so let's come to magnetic field. Magnetic field, it is a vector field in the neighborhood of a magnet, electric current, or charging electric field, in which magnetic forces are observable. Okay, so what this one is trying to tell us that magnetic field is a vector field. But first, we must know what is a vector. A vector is any magnitude, like force. So let's say a force of value 11, which has displacement or which has a direction. So any magnitude that has a direction is a vector. So coming back to this definition, magnetic field is a vector, any magnitude with direction. So it is a vector field in the neighborhood of a magnet. So what we are trying to say is if we have a magnet here, uh, so the vector field that is around this magnet or in its neighbor, like neighborhood, like normal neighborhood, in the around near this magnet or electric current or charging electric field in which magnetic forces are observable. Okay, so magnetic field is just uh, uh, the around the neighborhood. It is the vector field around the neighborhood of a magnet in which we can feel the magnetic force, or in which we can feel the magnitude or the power, like let me say that way, the power, or we can feel the strength of the magnets. That is briefly what is described as magnet. So basically, around this magnet or any place around this magnet that we can feel the magnetic force, or we can feel the power, or we can feel the cause, anything like attraction or something that is caused by this magnet is what we call magnetic field. The area around which we can feel the force of the magnet, or the power, or the cause of the magnet, that is what we call magnetic field. Okay, so let's come to magnetic force. Magnetic force is an attraction or repulsion that arises between electric charge particle because of their emotion. So if we have a magnet here, oh my drawing, if you have a magnet here, uh, the attraction or the ability of the magnet to attract or repel, that arises because there is an emotion of electric charges. That is why what we call electric force. Basically, any attraction or anything like any attraction or repulsion that arises or that is caused between electric charge particles because of the movements of electric charges, or the movement of electric uh, particles. That is what we call magnetic force. And it is the basic force responsible for such effect as the motion of electric motors and the attraction of magnets for iron. So that's the force that is exerted when uh, electric motors they make movement, or when a magnet is able to attract an ion. Yeah, so if your magnet attracts, if you put an ion close to a magnet and it attracts it, it is that force that comes to being. Or if you put another magnet to close to another magnet and it repels it, it is that force that comes to being. Okay, so let's continue. Electric forces exist among stationary electric charges. Okay, so take notice of this. Uh, he's saying electric forces, not magnetic forces. Magnetic forces do not exist among stationary electric charges, but electric forces, that one is possible. Electric forces, we have different kinds of uh, electric forces. We have what we call uh, what we call electrostatic force between stationary charges. So electric forces can exist among stationary electric charges, but not magnetic force. Okay, so to take a good notice of that one. And also, it says a magnet has two poles. So we know that every magnet has two poles. We have the north pole and we have the what we call the south pole. So he's saying the north pole is that and which points toward geographic north when the magnet is freely suspended. So anytime we suspend a magnet freely, anytime we suspend a magnet, not that we are putting a magnet on the ground, no. Anytime we make the magnet to suspend in the atmosphere or in the air freely without any force against the magnet points east north pole to the north, the north or the north of the geographic north, like the north part of the earth. That's how compasses work. That's how they are able to tell where is the north, where is the south using compass. So anytime we rest a magnet freely in the atmosphere or suspend a magnet freely, the north pole points to the geographic north. And also we know that like poles of two magnets repels each other, whereas unlike poles attract. So if you have a magnet and uh, you bring the north pole and the north pole of the other magnet together, it will repel. But if uh, you bring opposite poles, like unlike poles, like north and south together, it will attract. So that's another property of a magnet. The next slide. You say electric and magnetic forces exist among moving electric charges. So anytime there's a movement in electric charges, both electric forces and magnetic forces, they all exist among those electric charges. So anytime you see an electric charge moving, magnetic force is in action, and electric force is also in action. And he's saying the magnetic force between two moving charges may be described as the effect exerted upon either charge by a magnetic field created by the other. Okay, so yeah, from here we know that the magnetic field around elementary particles is a basic electric uh, a basic characteristic of the particle, just as their mass and electric charges are intrinsic properties. And also, we know that the magnetic field of all the electrons in certain material add together to give a resultant magnetic field around it. Let me explain this one a bit. Here he was saying that uh, the magnetic field around all electrons. So each electrons summing up their magnetic field together adds up to get to give us the resultant magnetic field of the magnet. So in case we have some small magnet like this, uh, each magnetic field of the electrons, if each part of them sum up to give the magnetic field of this magnet. So if each magnetic field is one, it we add all of them together, and I think we get something like around seven. Yeah. So the magnetic field of each electron in a certain material adds together to give the resultant magnetic field of the whole material, or the magnetic field around that magnet that we are talking about. And also, he said, however, in other materials, the magnetic field of all the electrons cancel out, so giving out no resultant magnetic field around the material. So there's a possibility that all the magnetic fields around this magnet will cancel themselves to the extent that we get no magnetic field again. The magnetic field will be zero. That's what he's trying to say. However, in other materials, the magnetic field of all electrons cancel each other. Yeah, so here, yeah, he's trying to talk about uh, materials that are non-magnetic. So all these materials, like for these materials, the magnetic fields they cancel each other. And also he said magnetic field of this magnitude is a vector quantity that can be defined at a point in terms of the velocity of the moving charges. Okay, so and the force that acts on on the particle. So from this slide, I told you that as we define the magnetism as a phenomenon associated with magnetic fields which arise from moving motion of electric charges. I told you that vectors are a resultant of magnitude times the velocity or the displacement. Yeah, so here that's what he's trying to tell us, that magnetic field of this magnitude is a vector quantity that can be defined at a point uh in terms of the velocity, the displacement over time. I'm going too deep into physics. Velocity, which is displacement over time of a moving charged particle, and the force that acts on the particle at that point. So we can tell the magnetic field by the velocity of the particle, of the moving particle, and the force that acts on the particle at a particular point in time. Okay, so here he's saying when an electrically charged particle move moves with a velocity v through a point in a magnetic field. A magnetic force F is exerted on the moving particle provided the velocity is inclined to an axis through the point. So uh, he's saying when an electrically charged particle, electrically charged particle of charge q. So here q is the charge of the particle, moves with a velocity v. So this the speed or the displacement per time of the particle is v through a point in a magnetic field. The magnetic force exerted, the magnetic force that is experienced on the moving particle is provided uh, on the moving particle provided the velocity is inclined to through the axis to an axis through the point. Yeah. Let me take it all over again. Okay, when an electrically charged particle of charge q moves with a velocity v through a point in a magnetic field, a magnetic force b is exerted or experienced on the magnetic particle provided the velocity is inclined to an axis through the points. Therefore, the magnetic force is proportional to the charge q of the particle. Okay, so he's saying if this condition occurs, the magnetic force is proportional to the charge q of the particle. The magnetic force on a negative charge is directed opposite to the force of uh, a positive a positive charge moving in that same direction. So he's saying if this condition occur and the magnetic force on a negative charge is directed opposite, so the magnetic force is directed opposite to the force uh, on a positive charge moving in that same direction. Okay, so if a magnetic force on a negative is directed opposite to the force on a positive charge moving in that same direction. Okay, so the magnetic force is proportional to the magnitude of the magnetic field B. The magnetic force is proportional to the speed of the particle. The velocity vector makes an angle with the magnetic field. The magnitude of the field or the magnitude of the magnetic force is proportional to sine theta. Okay, so from all these things that he has described, we get the magnetic force from here. It's in when an electrically charged particle of charge q moves with a velocity v through a point in a magnetic field. The magnetic force exerted. So this is the magnetic force exerted. Then he's saying the magnetic force is proportional to the charge q. So here we know magnetic force is proportional in mathematics, proportional, directly proportional. Okay, so this is the magnetic charge, and it is directly proportional to the magnitude of the force or the magnetic force. And the velocity is also proportional to it.